Of all the continuous distributions or continuous probability distributions possible, the most widely used and most relied upon is that of the normal distribution. And so we're going to spend quite a bit of time here in Chapter 7 discussing the normal distribution and how we handle it and how we can take information from it. Now, to start, what I want to make clear is that there is not the normal distribution, there is a normal distribution. And in reality, this is a family of distributions. Okay, and this is important to keep in mind in that there are really infinite numbers of, or an infinite number of normal distributions possible. And they all share certain characteristics, but our results are different depending on which precise distribution we are dealing with. And so to highlight that, let's just look at a few. So we could draw a normal distribution, something like this. That'd be the best one I've drawn. And this would have, maybe this has a mean of 12, so the center of that data is 12, and it has a standard deviation of, let's say, 4. We're going to actually move this down because I realized I wanted a little more space. And that, so we have a mean. Let me just say the mean is 12 and the standard deviation is 4. And for a normal distribution, that's all we need to be able to describe it. Okay. What is true about a normal distribution? Well, there's 3 big aspects that we want to just touch on. So number one, there's a bell shaped to it. Okay, and so what that means for us is that we can recognize it in some sense. We see that typical bell shaped of the normal distribution where it kind of has that nice double curve going on. Mathematically, we have some convexity and concave going on, and we have kind of a, you can see it ramping up, and then it starts to slow down, and then it curves back down, and then all of a sudden it shifts and speeds up in some sense. It's kind of a roller coaster mentality. So they're bell-shaped. They are symmetrical. So this is going to become incredibly useful for us in that we can think about probabilities, knowing that half of the probability falls to one side of the mean and half falls to the other side of the mean, right? So because it's symmetrical, this can kind of fold on itself, and half of the probability, remembering that underneath the curve is always equal to 100%. So 50% of it must fall on one side of the mean and 50% on the other side, because those are equal. As I have tried, and obviously this tail doesn't go. Maybe I'd drag that out. It's supposed to look the same on both sides. So that's going to be helpful. Another way to think about that is the skew is 0, if you want to recall from previous chapters. The other thing is that they're asymptotic. Remember all the T's in there. And I've failed on this, because what asymptotic means in our situation here is that this never actually does touch 0. So asymptotic just means it's getting closer and closer to a value. In this case, that value is 0. So the likelihood of any outcome never actually touches 0. It just goes off infinite, getting closer and closer to 0. So that's going to be helpful to remember or to think about when we think about extreme outcomes. And we'll get more into that in the next few chapters. But one thing to note is that so this is just one possible distribution, okay, which I've drawn on twice. Let me try to get rid of the red here. And so we could have other distributions. Put the blue back. Okay, so we could have another distribution. Let's change it to orange. And if let's see how well I can do again. So we could have another normal distribution, and this is equally as normal, although I did a worse job drawing it. But this also has a mean of 12, and maybe it has a standard deviation of 3.5. Okay, it's a little tighter standard deviation. It gets thinner and taller. Again, the area under orange, the orange curve, has to also be 100%, just as it was with blue. So as you scrunch it, it's going to grow taller, and so that the area, in some sense, this area up here makes up for the loss of the area on the outside here. One way to kind of think about it. So those are two distributions, both normal distributions. We could also have a normal distribution out here, so something like this, where let's say the mean here is 17, and we'll keep the standard deviation. If I drew it kind of well, let's say that's also 4. So the standard deviation in this case between the blue and the yellow are the same, but the mean has shifted, so it's a new normal distribution. So what I'm trying to highlight here is that there are as many means and standard deviations. Any mixture of those produces a new normal distribution, and so there really are just infinite numbers. We could pick any values in between those or beyond those. So as we've been doing with continuous distributions, we want to summarize these with the mean and the standard deviation. Now, a lot of times we are kind of given this information with a normal distribution. If we had data on it, we could try to crunch it and kind of come up with this. But a lot of times the way we deal with normal distributions is we're already aware of the mean and the standard deviation. And we can depict that, right? So we can draw that on a graph. But we want to think about areas or ranges of outcomes, right? So again, what we might be curious about is what's the likelihood in this, maybe in this blue distribution. We're curious about the likelihood of being between certain outcomes. So maybe that's, between 7 and 8. We're curious about the likelihood that you fall within that range. And so we're going to have to do some math to get there. Now, as we've talked in previous videos, the way we would do that is to sum up that area. Again, remembering that the total area under the curve is 100%. And so this share between, if we said 8 and 9 here, that share would be the area of that under the curve between those values. Now we can't, like in the uniform distribution, we simply did base times height. Can't quite do that here. We don't know the height or it's not one even height. So we would need to do some more complex math. And the way we would typically do it is to integrate. So for those of you that have taken calculus, you'll notice that all we're really doing here is integrating from 8 to 9. But to do that, we need to know the formula of the line. And so the formula of the normal distribution is a little gross to look at initially, but I'll write it down here. And we're not actually going to do this. We're going to find kind of a shortcut to doing this. But is that going to show up? That's going to be hard to read. Let's pick a different color. So the formula, P of x. So what is the probability of, of course, so let me just verify. This is P of x for any of these, right? So the probability associated with an x so what is the value at any particular x? It's written out as, we can write it as the sigma times, or 1 over sigma times the square root of 2 pi. Okay, e to the negative x minus mu squared. Okay, again, we're not going to have to deal directly with this formula, but I do think it's instructive to see, number one, how gross it is, so we don't want to deal with it if we don't have to. But number two, that you do have, some sense of everything included here. We have, what are we putting in here? We're putting in the mean, the standard deviation, which we also shows up as the variance here. And then we also are using pi 3.14, and then e, well, the full pi, not just 3.14, but then e 2.718. So both of these are just mathematical constants. So we can plug that in. So you could even do this. It's even easier if you go to something like Wolfram Alpha and just plug some values in. But let's say I want to worry about this yellow distribution here. I could plug in various points. So if I want to know the height at x equals 18, I can plug that in or crunch this formula, plugging in, you know, the mean of 17, standard deviation of 4, and if I went through all the math, I would get something that tells me that the height here is about, so at 18, so the p of 18 is something like 0.0966 repeating. And so we could do that again with other values. 18.3 or 18.3, right? We could do it for every x, so at 18.3. So we do not need to do this, but I want you to understand that this formula is giving us the normal distribution. And so this becomes 0.0946. Okay, so slightly less. So as we move along, it drops a little bit. And we could do that for every value of x. Now, that's essentially what integration is going to do on the finer and finer scale. We would be able to add up all of those values. So that would be the process of going through it. Now, we don't have to do that because of what is referred to as the standard normal. So we'll be back with another video discussing the standard normal and how and why it helps us out along our process.